Hello students, welcome back. Please remember, here we are going to cover two objectives. One is associated to the relationship between the signs of the derivative versus increasing decreasing nature of the original function. And that's something we discussed earlier, and we're going to deal with the second objective shortly. But before that, let's have a short summary of those. Here's a summary table. Original function is increasing when the derivative is positive. Original function is decreasing when the derivative is negative, and when the derivative hits 0, then we have critical point. And here, increasing, that means we have to have positive slopes all the way. In any case, always positive slope. Always the tangent line is pointed upward because the original function itself is going up. So increasing means positive derivative. On the other hand, decreasing means negative derivative. Graph is going down, and look at these, all this tangent line segment here. No matter what you do, always point it downward because original function itself is going downward. So the slope is negative, therefore negative derivative. So plus, then increasing, minus, then decreasing. What if we hit 0, then we can have critical point. Or derivative doesn't exist, and again, critical point. Anything can happen. But the last case is rather nasty, so don't worry too much about it, because after all, this is just 1325. Now look at sign. Sign changes from minus to plus. Derivative changes from that minus to plus, then you have local minimum. Derivative changes from plus to minus, then local maximum. And stays positive or stays negative, then we have critical value that is neither maximum nor minimum. That was a quick summary. Now let's go to the next objective. This is going to be a bit harder. Let's look at the concavity. Here we go. The original function is concave up if the derivative function is going up, or equivalently speaking, the second derivative is positive. Original function is concave down when the derivative is going down, or equivalently, second derivative is negative. Understanding the behavior is going to be challenging, but it is not difficult to memorize actually. You see, up is up and down is down. Derivative goes up, then original is concave up. Derivative goes down, then original is concave down. It's easy to understand. Excuse me. It's not going to be easy to understand, fair warning, but it's easy to memorize. Up is up, down is down. Now, what about understanding? Well, okay, here we go. We have various situations of concave up yet increasing. Here, concave up yet decreasing. Here, concave up around local minimum. Now, let's look at some animation. For simplicity, I'm just doing the middle part. Still, you'll be able to understand things here. Look at the line segment here. Red line segment. What's the slope? It's very negative. You see that? Graph here is pointed downward around here, and then this red tangent line segment is pointed downward too. So slope is very negative. But let it run, and let's see what happens. What do you see? It used to be very negative, but gets bigger, 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 and then hits 0, horizontal tangent, and keeps on getting bigger, 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 so that we end up with very positive slope. Let's go down here. Very negative. Oh, stop. Very negative here, but gets bigger, 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 and then slope is now 0. And then keeps on getting bigger, bigger, bigger. Now slope is very positive. And I did some color coding as well. It starts off with very red, and then gradually it's going to lose color, and then it's going to change to blue. So very negative, and increase, 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 and hit 0, and then get bigger, 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 and ends up with very positive. So what are we looking at here? Concave up, graph is bent upward, is associated to increasing slope. Increasing first derivative function. So the first derivative function is going up, means the original function as concave up. A bit hard to understand. Yeah, I understand that. It's not an easy concept, but it's not difficult to memorize. Up is up. That's about it. And as for the second derivative, this is derivative of this first derivative function. So use prior logic here. It's going up, so that's its derivative is positive. And here's a visualization for concave down. Here we can see various types of concave down and decreasing, concave down around local maximum, concave down yet increasing. In any case, graph is bent downward. Now let's run the animation. Goes like this. It used to be very positive. Look at the color coding as well. Used to be very blue. And it's getting smaller, 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 and then hit horizontal tangent where the slope is 0. And then keeps on getting smaller, smaller, smaller to negative. So it ends very red, very negative. Let's stop it here. Used to be very positive. Slope is very positive. Slope is getting smaller, 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 and then becomes 0, and keeps on getting smaller, 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 and ended up with very negative. Make sense? Again here, used to be very positive, and going down, 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 down to 0, and keep going down, down, down to negative. Look at the slope. In short, the slope gets down, or the derivative gets down, means concave down. Again, I'm not trying to make everybody understand everything. It's a difficult concept, but everybody should memorize the end result. That's not difficult. Up is up, down is down. And then here's a summary, by the way. Concave up, then derivative is going up. And up, so its derivative, the second derivative is positive. Concave down, then derivative is going down. And it's going down, so that's derivative. The second derivative is negative. Now, there's something called inflection point. What do you mean by inflection point? Inflection point is the point where concavity changes, like this. Used to be concave up. Now, after this, concave down. Used to be concave up. After this, concave down. Used to be concave up. Now, after this, concave down, like that. Now, inflection points. Well, if you have inflection point, then the second derivative will turn out to be 0, because basically this is where, let's see, if you look at the derivative function, and derivative is actually increase, 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 and that hits maximum here, and after that is decrease, decrease, decrease. So inflection points actually corresponds to the local maximum, local minimum of the derivative function. Do we have that animation here somewhere? Yeah, I guess so. So inflection point around here. No. Inflection point is around here, right here. That's when the slope is the biggest. It used to be pretty flat here. I mean, slope is always positive here in this graph. Graph itself is always going up, so no question there. But the line segment is pointed upward. And then the slope is getting bigger, 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 bigger. And it hits a maximum here, and afterwards, slope gets smaller, 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 smaller. At the inflection point, the slope, or the derivative function, hits the maximum. And also vice versa as well. But in practice, inflection point at second derivative equal to 0 is going to be sufficient for most people. It's a tricky business. Okay, I'll try to solidify your understanding through graph problems in section 2. For now, let's stop here.